Precipitation reactions. So hard water, and around here the tap water is considered hard water. Hard water contains calcium ions and magnesium ions that are dissolved in the water. And this is not a bad thing for your health, because you do need calcium and magnesium, and your body can get some of that from the water. It is bad if you're in charge of keeping your house clean, because the calcium and the magnesium will react with soap and form scum. It's called curd, a bathtub ring. It's this soapy, scummy thing that forms in the bathtub. That can also happen in your washing machine. If you use soap to wash your clothes instead of detergent, you'll get that scummy stuff forming on your clothes. And then your white clothes become gray and dingy. So laundry detergents have sodium carbonate in them to help get rid of the magnesium and calcium ions. So calcium carbonate, we look at our solubility rules, calcium carbonate is insoluble. Magnesium carbonate is also insoluble. So the carbonate from the sodium carbonate in the laundry detergent precipitates the calcium and the magnesium ions so that they can't make that soap scum, that gray curd, with the soap. So a precipitation reaction is a reaction in which you have a solid that forms when two solutions are mixed. So here's a picture. So here we're pouring this clear, colorless solution into another clear, colorless solution, and we've got this yellow, opaque, cloudy thing forming. It's cool, right? We saw some stuff like this with our copper cycle lab. It's fun. We can't see through this because it is a solid. It's very tiny particles of a solid. If you wait, they will fall to the bottom. They will precipitate. So the precipitate is the solid that forms. This is a description of what's happening here. We've got potassium iodide, which is soluble, and we're mixing it with lead nitrate, which is also soluble. When we mix those two together, the lead and the iodide together are an insoluble compound. And so they're going to form this yellow solid and fall to the bottom of the flask. Potassium nitrate is also soluble, and so it's just going to stay in solution. How do we predict what the products are? Well, you look at the original solutions and see what are the ions that are present. So here we had potassium iodide solution and a lead nitrate solution. So in the potassium iodide, you've got potassium ions and iodide ions. In the lead nitrate solution, you've got lead ions and nitrate ions. And so what you do is you exchange partners. So this ties into my feelings that metals are masculine and nonmetals are non-masculine or feminine. So this is the guy and this is the girl. And I like the book, they made it blue and pink, right? So this is the guy, this is a girl, this is a guy, this is a girl. So this is like two couples, and they might not be like going steady or anything, but you know, we're going to this party. I brought a friend of the opposite sex. Maybe you got a +1 on the invitation. You didn't want to go by yourself, so you took this person that you don't hate, right? Okay, so they come to the party. When they all mix together, what we're going to do is we're going to swap the partners and see if there's any chemistry, right? You know, sometimes you just meet somebody and you're like, oh, this is the best person ever, right? It can happen. So here what happens is, so we're going to try these different partnerships here. So let's try potassium with nitrate. Well, we tell if they're going to really, really like each other by looking at the solubility rules. Potassium and nitrate are going to be a soluble compound. So it's not that they hate each other or anything, but they're just still going to be mingling and swimming around in this party beaker here. Okay, lead and iodide, though, you look that up in the solubility rules. Lead iodide forms an insoluble compound. The lead ions and the iodide ions are really, really attracted to each other. And so they're going to stick together. In the party analogy, this is like they go off and they find a couch on the back porch, and they're sitting there just, you know, whispering sweet nothings, making out, doing something. They're out of the party. You're just not even going to see them. They're still there, but they're just off to the side, right? So there was a chemical reaction that occurred there. A precipitate formed. That does not happen every time you mix two solutions of aqueous ionic compounds. There has to be a certain combination in order for that to happen. So if you've got potassium iodide and sodium chloride solutions, you mix those. We try swapping the partners. We look at potassium. Well, let's look at it here. We look at potassium and chloride. Are they going to hit it off? Are they going to be an insoluble compound? No. We look at sodium and iodide. Are they going to hit it off, make an insoluble compound? No. So it might be a great party, but there were no relationships that came out of this. Okay, there was no chemical reaction. So we need to learn how to write chemical equations for precipitation reactions. You start out by writing the formulas for the two reactants, and then below the equation, write the formulas of the products that could form from the reactants. And I'll show you how I like to do that. Then you're going to look at the solubility rules and see if either of those possible products is insoluble. If all the products are soluble, you just write no reaction, or we sometimes even abbreviate that further and just do N period R period. But if any of the products are insoluble, then we have to write the formulas for everything, indicating their states, solid or aqueous, and we have to balance the equation. So let's do an example. Write an equation for the precipitation reaction that occurs, if any, when ammonium chloride and iron 3 nitrate are mixed. We need the formulas for the reactants. Well, these are ionic compounds, so to write the formula for the ionic compound, we need the ion formulas. So ammonium chloride. So that's ammonium ion. It's NH4 plus because it is. And chloride is Cl minus because of its position in the periodic table. You look at those and you see, well, I've got a +1 and a -1 charge. All I have to do is put them together to write the formula for that compound. Is that soluble? Yeah, ammonium compounds are always soluble. So I'm going to put AQ after it because it's aqueous. It dissolves in water. Plus iron 3 nitrate. Well, iron 3 is iron 3 plus, and NO3, nitrate is NO3 minus. So we put those together. We need 3 nitrates to balance the charge on 1 iron. So we've got Fe, NO3, 3. And then, is that soluble? It is soluble. All nitrate compounds are soluble. That's the second rule. So this is soluble. A good way to help yourself learn the solubility rules is when you're doing problems like this, try to figure it out without looking at a list. Then check the list. But don't just go straight to the list. Try to remember first. So there's the first step. We've got the reactant formulas. Now, to write the formulas of the possible products, we're going to think about, these guys are going to swap partners. So ammonium came with chloride, and they're aqueous. There's no special attraction between them. Iron 3 and nitrate came together, again, aqueous, no special attraction. But let's see what happens with ammonium and nitrate. Maybe they're going to hit it off. Or with iron 3 and chlorine. Maybe they're going to hit it off. So I'm going to rewrite these partners over here. The metal always goes first, the cation, because it's Mr. and Mrs., just by convention. And you have to have a positive ion and a negative ion together. You can't put the two metals together because they both have positive charges. It's electrical. They're going to repel each other. The analogy does break down in some places. So I'm going to try ammonium with nitrate, and I'm going to try iron 3 with chloride. Ammonium and nitrate. Is that combination going to be soluble or insoluble? That'll be soluble. How about iron and chloride? Well, I hear people saying insoluble, but let's go back and look at the rule. So here's chloride. Chloride compounds are soluble except with silver, mercury 2, that's actually mercury 1, or lead 2. So they're both soluble. So there's no reaction. Pardon me?
Because they're polyatomic, you're not going to form no H2O.
They're not going to, we're not going to make any water molecules or anything. The ammonium and the nitrate ion are going to stay intact. They're just going to possibly switch partners, is all that's going to happen. So that was no reaction. That's always fun because then you could skip the rest of the steps. Let's do another one. Write an equation for the precipitation reaction that occurs if any when sodium hydroxide and copper 2 bromide are mixed. So we take the names, sodium hydroxide, and so we write the formula with the charge for the sodium ion, formula with the charge for the hydroxide ion, and then we put them together, and we ask ourselves, is this soluble or insoluble? Well, it's got sodium in it. All sodium compounds are soluble. And then we've got copper 2 bromide. So copper is Cu. The Roman numeral 2 gives me the charge. And bromide is Br minus because it's in group 7. So put these two together. Cu, Br2. Is that soluble? Going down the list, we've got the alkali metals and ammonium. We've got nitrate and something. Anyway, then next down is bromide, chloride, and iodide. Copper is not one of the exceptions, so this is soluble. Now we're going to swap partners and see if anybody really hits it off. So I'm going to write sodium next to bromide. Is that going to be soluble or insoluble? That's going to be soluble because all sodium compounds are soluble. So let's try copper 2 and hydroxide. As you go down the list, neither of those is in the top part of that table. You get down, hydroxide compounds are generally insoluble. Copper's not one of the exceptions. So this is going to be insoluble. We have a solid, we have to finish this. So I'm going to write the sodium bromide formula. That one was aqueous. And here we're going to have Cu, bless you, OH2, and that's going to be a solid. Okay? Then we have to balance the equation. Over here I have one sodium, over here I have one sodium. Over here I have one hydroxide ion, over here I have two hydroxide ions. So I need to go back to the sodium hydroxide and put a 2 in front of that. That fixed the hydroxides, messed up the sodium. Now I have 2 sodiums, and over here I only have 1, so I have to put a 2 over there. 2 sodiums. So I've got sodium and hydroxide straightened out. Here's copper, 1 copper, 1 copper, 2 bromines, 2 bromines. Done. Any questions? I'm giving you little pieces, right? And now we're starting to put the pieces together. If you haven't figured out nomenclature yet and these ions and how to stick them together and write the formulas, this is going to be pretty much impossible to do. So if you're still struggling with nomenclature, go back and work on that. Ask me questions, get some help.